what does the second derivative do to our graphs? So, a couple little definitions first. If the graph lies above all of its tangents on an interval I, then it's called concave upward. If the graph lies below all of its tangents on I, it's called concave down. Okay? Look, it's a lot easier to see with a picture. Concave up looks like a cup, or even just a piece of that cup. Now, when they're talking about all these tangent line stuff, look, if you draw tangent lines, no matter where you draw it, notice they always fall completely below the graph. So the graph lies above all of the tangent lines, it's concave up. But it's easiest to me to think about it as like a cup. And it could be just a little piece of it, right? So it could be just that piece. It doesn't have to be the whole cup. Okay? But if you kind of in your mind extended it out, that's what it would look like to be concave up. We have a lot of different examples. I mean, you know, exponential functions will never have that cup look, but they have this, right? And all of the tangent lines lie below it, and it kind of looks like that piece of a cup. Same thing with the concave down. The most dramatic example would be something like this, and you can see again, if you draw tangent lines, no matter where you draw one, it's going to be above the graph. Okay? So if the graph lies below all the tangent lines, it's concave down. But it's a hill or a piece of a hill, upside down cup, whatever. Okay, you know, your graph might look something like that, but it's a hill or a piece of a hill is what makes that shape kind of concave down. Okay, think of it, it holds water, water runs off of it. Okay, however you want to phrase that in your mind. Okay? But the second derivative is going to tell us about that kind of thing, whether it's going to be concave up, concave down. Now, the last definition thing that we have is about an inflection point, and I've mentioned it before. So a point on a curve is an inflection point if it's continuous and it changes from concave up to concave down. So you might have a graph that is concave down, and then at some spot here it switches to concave up. That spot is the inflection point. Okay? Right where it changes from concave up to concave down. Or it could change from concave down to concave up. Okay? And in that spot, that's the inflection point. But it has to go from one to the other. All right, so the second derivative tells us that if the second derivative is greater than 0, it's concave up. If the second derivative is less than 0, it is concave down. Okay, so greater than 0, concave up. Less than 0, concave down. So let's look at an example real quick. Say, okay, we need to figure out what we've got going on here. So if we're thinking about it being concave up, we need the second derivative, right? So first derivative is 3x squared minus 9, and the second derivative is just 6x. So 6x is greater than 0. We want to look at that inequality. Well, in this case, it's where x is greater than 0. So on the interval from 0 to infinity, it is what, concave up. And then if we want to look for concave down, where's that second derivative less than 0? So that's when x is less than 0. So that's from negative infinity to 0. It is concave down. right. So here's an oddball question for us. Just wanted to throw it in there. See about your sketching skills. So we're going to sketch a possible graph that satisfies all of these conditions. Well, what I would do is start off with just a number line. And at all of these spots where it talks about these particular intervals, okay, I'm going to put all of those endpoints somewhere on my number line, okay? So negative infinity, of course, doesn't go on there, but we could have 1 on the number line from 1 to infinity, so that's still a 1. So infinity to -2, so -2, and then 2 to infinity, then between -2 and 2. Now these limit ones, so remember all of these intervals that I have highlighted, all of these things are x-coordinates. Right? However, these things are y-coordinates, right? Okay, so if that limit goes out, as it goes to a negative infinity, it gets closer and closer to -2. That means we have a horizontal asymptote at -2. And then at 0, we have a horizontal asymptote as it goes out toward the positive side. Okay. Now, back to my x-coordinates though. The first derivative from -infinity to 1 is going to be increasing. So notice I actually have 1, 2, 3, 4 intervals to worry about, and I'm going to take them kind of one at a time. Okay, so from -infinity to -2, it's increasing there, and it's increasing there because we've got to get all the way up to 1 for it to be increasing from this part, and it's decreasing from 1 to positive infinity, so from 1 to 2 it is, and from 2 on out, that's decreasing. Now the second derivative tells us the concavity is greater than 0 from -infinity to 2. So on this interval, it's greater than 0, so it's concave up. On 2 to infinity, it's concave up. And then when it's less than 0, that means it's concave down, right? And that's just between -2 and +2, so both of these intervals in between there is concave down. So now, if it's increasing and concave up, the shape of the graph is this. If it's increasing and concave down, the shape of the graph is this. Okay, now it might be a little steeper or something like that, but notice it's still headed uphill and it's concave down. So then downhill and concave down would be this shape, headed downhill, and then downhill and concave up, it's kind of this shape. So I just need to piece those together and keep in mind I have these asymptotes. So let's see, at -2 and 1 and 2 are my important parts. All right, so it is here, it's concave up until it gets to this point, and then it continues being increasing, but now it's concave down, so it's going to do this. Okay. Now it's going to be concave down and decreasing, so it's going to have that kind of shape. And then it's going to be concave down and decreasing, but I have a little bit of a fault here because if it's decreasing, that's never going to get to 0, right? So all that tells me is I need to be above that line, okay, when I get to that side of things. So let me make my graph a little bit taller there. It's going to be increasing concave down. Then it comes down with that little shape. and then it levels off like that. So there's a possible graph. Okay. Now there is no one right answer to these. Every one of our graphs could be different as long as it has these shapes. And for me, I always need to have this little number line laid out with my arrows and my cups and hills so I can kind of see what's going on. All right, so let's try to put both this one and the first derivative stuff together and see if we can sketch some kind of ugly graph. Now really all I'm going to look at the properties of is the concaves up and the concave downs. Okay, so first thing I need to do, find the derivative. Okay, we're going to need a product rule here, so that's going to be 2/3 x to the negative 1/3 times 6 minus x to the 1/3 plus x to the 2/3 times 1/3 times 6 minus x to the negative 2/3 times negative 1, because we've got the chain rule there, right? If I'm going to have to take a second derivative, I'm going to try to simplify this as much as I can. So just looking at a couple things here, that negative 1 is just going to change that to a minus. So I can kind of forget about that, okay? So let's just erase that. Let's just stick a minus there from that negative 1. Now, remember we talked about in one of the other videos factoring things that have common factors, but these exponents are kind of wacky. So picking the smallest exponents and the smallest coefficient, I'm going to factor out 1/3 x to the negative 1/3, because the negative 1/3 is smaller than the 2/3, and then a 6 minus x to the negative 2/3, and that's going to leave me on this first one 2/3 divided by 1/3 will just leave me with a 2. That whole term with the x factors out, and then we're left with a 6 minus x to the but we got to take that out, so 6 minus x. To get that exponent, remember we're doing a 1/3 minus the negative 2/3. And that would be 3/3, which would just be 1. And then we'll subtract, and we'll have 2/3 minus the 1/3 to get the x. And then we'll just continue simplifying. So that's 1/3 x to the negative 1/3, 6 minus x to the negative 2/3, and then 12 minus 2x minus x. And if I simplify that, what do we get? 12, oh yeah, look, 12 minus 3x, I could factor a 3 out. And then that would leave me with 4 minus x. And then notice this is kind of nice. The 3 times the 1/3 give me a 1. So f prime of x, after all of that work, you're going to have a 4x, 4 minus x in the top, and then the bottom, an x to the 1/3, and 6 minus x to the 2/3. Now we got to get critical point. So critical points, the numerator has to be equal to 0. So when is 4 minus x equals 0? Well, that's when x equals 4. Then we also have to have the denominator equal to 0. So another one's going to be when x to the 1/3 equals 0, so x would have to equal 0. And then another one when 6 minus x to the 2/3 equals 0. So 6 minus x is 0, x is equal to 6. So those gives me 3 critical points there, 0, 4, and 6. Now, good gracious, we're going to have to do the second derivative. Oh, good gracious, the second derivative. Well, do you want to take my word for it? Or you want to work through all of it? So the second derivative, you got to use the quotient rule. And inside of there, you're going to wind up with the product rules and stuff like that. It's going to be negative 8 over x to the 4/3 and 6 minus x to the 5/3. And so where we check to see with concavity and stuff, that's just going to be again where x equals 0 and 6 from where this stuff is undefined. Okay? Alright, so those are really the super important points at the moment. So I need to see where this thing's increasing, decreasing, concave up, concave down. So 0, 4, and 6 were all the important points there. So I need to pick test points. So I think I'm going to pick -1, 1, 5, and 7. So remember, I have to have one in between all of them and also out to the edges. And I need to test the derivative and the second derivative. Okay? So if I look at derivative, and probably the easiest way to do this at this point maybe is, use your calculator and stuff. But when I do the first derivative at -1, so hold on a sec. Okay, so I took a second there, stuck those in my calculator, just so I can use my calculator to evaluate these, because we really don't want to spend a whole lot of time trying to do this stuff by hand. So I want the first derivative and the second derivative there. And I'm just going to, instead of doing the inequalities and stuff, I'm just going to pick these test points. So if I evaluate the first derivative at -1, this turns out to be a -1.3. And then if I do the second derivative, oh, hold on a second. Second derivative. Hold on, I'm having issues with my calculator. All right, there we go. And calculate value at -1. That blasted, it did the first derivative again. Okay. There we go. Okay. And we are at -0.3. So what that tells me is on this interval, my graph is downhill and it's negative, so it's concave down. Now from 0 to 4, I'm just going to pick, my test point was 1, right? So when I test point 1, the first derivative, f of 1, is going to be 1.0 something. It's positive, that's all I care about. And my second derivative is -0.5. So it's increasing, but it's still concave down. Okay? And my next test point was at 5. So f prime of 5 is -0.58, blah, 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 blah. And then the second derivative at 5 is -0.9. So it's decreasing and it's concave down. And then my next test point was at 7. So first derivative is negative, f prime of 7 is negative 1.5, and then the second derivative is positive, so it's about 0.6, so it's concave up, so it's decreasing and concave up. Now, all of that information could give me a bit of a sketch, but I do want some actual kind of concrete points. So at all of these points 0, 4, and 6, I'm actually wanting to think about what the function is at those particular spots. Okay, so I'm going to kind of scroll back and forth to sketch my graph, but at 0, 4, and 6. So f of 0 is going to be 0. Okay, that one's easy enough because we got that factor. So f of, just making some notes here. So f of 0 equals f of 6. That was going to be equal to 0. And f of 4 what was my original function? Take a look at it. So I'm just going to put 4 into that sucker. In fact, really what I'm going to do is I'm going to actually pull up the graph of this thing and then use the calculator to evaluate it. And let me scroll back down so I have all this information, and then f of 4 is equal to 0 as well. All right. Oh, no, wait a minute. Wrong graph. F of 4 is 3.17. I thought that was kind of weird. So f of 4 is about 3.2. So now with all this information, I can get an ugly sketch. Okay, so I know from negative infinity to 0, it is concave down and decreasing. Okay. Oh, I don't have another page. Let's see if I can insert a page here. Okay, and then let me insert one of my little graphs. I want to make that a little bigger. All right, so at f of 0, the function was 0. 1, 2, 3, 4, it was 0, and at 6, it was 0. Okay, so from negative infinity to 0, it was concave down and decreasing. So with that being said, it's got to be concave down, decreasing, and it's got to hit that point. So it's concave down, decreasing, and it's got to hit that point. And it's decreasing the whole way, so I know it doesn't like switch to make some kind of nice smooth minimum like it does on a parabola. Okay, it's got to be that hill shape the entire time, and then once it got from there, it started being increasing until it got to 4, and then it was decreasing from there to 6, but it was always concave down. So from there, oh, my 4 disappeared. 1, 2, 3, 4. Okay, and at 4 it was 0 as well. So it's got to hit that point. Oh, and look, there was a maximum somewhere in there. Boom, because it did that kind of number. Now I guess the question is, where is that maximum? But I'm just doing kind of the ugly sketch. Now from 4 to 6, what was it doing? So from 4 to 6, I mean from, wait a minute, hold on. From 0 to 4, from 0 to 4, it was increasing concave down. Yeah, no, that was good. That was good. What am I thinking? So from 0 to 4, increasing, concave down. But at f of 4, it was... okay. F of 4 was 3.2. 1, 2, 3. So this point actually should have been up here. And this is what happens when I have to scroll back and forth. Increasing, concave down until we get to that point. Then it's concave down, decreasing till we get to that point. And then the rest of it, from 6 on, was in decreasing and concave up. So it was decreasing and concave up, so it's got to have that shape. So that is what that graph would look like in there somewhere. Ooh, that was a lot of work, wasn't it? So, anyway, we will actually get more onto this in the next section, which is dedicated completely to curve sketching. And we'll make sure we get all the kind of nice little details in there. So good luck, and let me know if you have any questions.